AI hallucination is when a language model generates text that is factually incorrect, fabricated, or unfounded, and presents it with complete confidence. It is one of the most important limitations of current large language models and a central concern in enterprise AI deployment. Let us examine why AI hallucination is such a fundamental challenge and what makes it so difficult to detect and eliminate. 5 properties of language models explain why hallucination is a structural challenge rather than a simple bug that can be patched away. The root cause of AI hallucination lies in how language models are trained and what they optimize for. A language model is trained to predict the next token in a sequence, to generate the most statistically plausible continuation of a given text based on patterns learned from its training corpus. This objective is not the same as generating the most factually accurate continuation. The model has no direct access to external facts or a ground truth database. It synthesizes responses from weighted statistical associations between concepts in its training data. When those statistical patterns happen to encode accurate information, the model produces correct outputs. When they do not, the model produces plausible-sounding fabrications. Language models are trained on large but finite corpora, which means their internal knowledge is uneven. Topics that appear frequently and consistently in the training data, major historical events, well-documented scientific concepts, widely covered news stories, are generally represented with high reliability. Topics that appear rarely, inconsistently, or only in low-quality sources, obscure individuals, niche technical details, recent events after the training cutoff, are the fertile ground for hallucination. The model must fill knowledge gaps with statistically plausible content, and without access to the actual facts, it often fills those gaps with fabrications that look indistinguishable from accurate responses. The long tail of human knowledge, the vast collection of specific facts, names, dates, citations, and details that are real but rarely mentioned, is where hallucination is most concentrated. A language model can reliably recall that the Second World War ended in 1945 because this fact appears millions of times in its training data. But ask it for the exact publication date of an obscure academic paper, the specific clause number in a regulation, or the precise founding date of a small company, and the model is likely to generate a plausible-sounding but incorrect answer. This pattern, reliable on high-frequency facts, unreliable on low-frequency specifics, is one of the most important characteristics of hallucination for practitioners to understand. A deeply problematic aspect of AI hallucination is that language models are generally poor at knowing what they do not know. A well-calibrated system would express high confidence when it is likely to be correct and low confidence when it is likely to be wrong. In practice, language models often express the same level of fluency and confidence regardless of whether they are about to state a well-established fact or fabricate a plausible detail. This miscalibration means that hallucinated content is stylistically indistinguishable from accurate content, making it very difficult for users to identify which model outputs require verification. Hallucination is not a fixed property of a model. It varies substantially across different models, different task types, and different domains. More capable, larger models generally hallucinate less frequently on common knowledge tasks, but may still hallucinate on specialized or recent knowledge. Tasks that require the model to synthesize information from a provided context, such as summarization and RAG, show lower hallucination rates than tasks requiring the model to recall information from its parametric memory. Some domains, mathematics, code, well-documented science, show lower hallucination rates than others, legal detail, biographical facts, financial specifics. Understanding this variation helps practitioners assess risk and apply appropriate controls for each use case. 4 essential terms that every practitioner needs to understand when assessing and managing AI hallucination. Confabulation is a term borrowed from neuropsychology, where it describes the phenomenon of patients who have suffered certain types of brain damage producing detailed, confident, but entirely fabricated recollections without any intention to deceive. The parallel to AI hallucination is instructive. Just as a confabulating patient fills gaps in their damaged memory with plausible fabrications, A language model fills gaps in its statistical knowledge with plausible token sequences that may bear no relationship to actual facts. The analogy highlights a key point. Hallucination in AI, like confabulation in neuropsychology, is not a sign of malicious intent, but a structural consequence of how the system generates output. Factual hallucination is the most consequential form of hallucination for enterprise AI deployment. It occurs when a model asserts specific factual claims, names, dates, statistics, citations, legal provisions, technical specifications, that are demonstrably incorrect or entirely fabricated. Factual hallucinations are particularly dangerous because they are delivered with the same fluency, grammatical correctness, and apparent confidence as accurate statements. A user without independent knowledge of the subject has no reliable way to distinguish a factually hallucinated response from a correct one through linguistic cues alone, making independent verification essential for any AI-generated factual claim used in professional contexts. Faithfulness measures whether a model's output is consistent with and accurately derived from the source context provided to it. The retrieved documents in a RAG system, the document being summarized, or the data extracted from a database. A faithful response stays within the bounds of what the source context says and does not introduce information from outside that context. Faithfulness is a distinct property from factual accuracy. A model can be faithful to a source document that is itself inaccurate. However, faithfulness is a highly desirable property in practice because it keeps AI outputs anchored to verifiable, auditable sources and dramatically reduces the risk of fabrication. Calibration is the property of a probabilistic system that reliably knows when it knows and when it does not know. A perfectly calibrated language model would express 90% confidence only in cases where it is correct 90% of the time, and 50% confidence only in cases where it is correct 50% of the time. In practice, language models tend to be overconfident, expressing high fluency and certainty even when generating hallucinated content. Improving calibration is an active research area, with approaches including training on uncertainty-labeled data, implementing explicit abstention mechanisms, and developing evaluation frameworks that measure the correlation between expressed confidence and actual accuracy. Let us now look at the practical strategies that organizations use to reduce hallucination risk in production AI deployments. For proven strategies that organizations combine to reduce hallucination risk in production AI deployments. Retrieval-augmented generation is the most widely adopted architectural strategy for reducing hallucination in enterprise AI. By supplying the model with retrieved source documents as context for each query, RAG shifts the model's task from memory recall, where fabrication risk is highest, to reading comprehension and synthesis, where faithfulness to provided context can be measured and enforced. When the model's response can be traced to specific retrieved passages, faithfulness evaluation becomes tractable. Automated tools can assess whether each claim in the response is supported by the retrieved context. RAG does not eliminate hallucination entirely, but it dramatically reduces its frequency and makes remaining errors more detectable. Temperature is the parameter that controls the randomness of a language model's token sampling process. At high temperature, the model samples from a broader distribution of possible next tokens, producing more varied and creative outputs. At low temperature, the model's sampling concentrates on the highest probability tokens, producing more deterministic, conservative responses. For factual tasks where accuracy is paramount, reducing temperature constrains the model to generate its most likely responses rather than exploring more speculative completions. While low temperature does not guarantee factual accuracy, a model can still consistently generate an incorrect answer. It reduces the variability that often produces hallucinated details and speculative additions. For high-stakes decisions where factual accuracy has significant consequences, medical diagnosis support, legal document review, financial advice, regulatory compliance assessment, human-in-the-loop review remains one of the most important risk mitigation strategies. Rather than treating AI output as a final answer, organizations deploy AI as a first-pass assistant that generates draft responses, summaries, or recommendations that are then reviewed and validated by qualified professionals before being acted upon. This approach captures the productivity benefits of AI while ensuring that consequential decisions retain human accountability and verification. The key design challenge is making the human review step efficient enough that it does not eliminate the productivity gains that motivated AI adoption. At production scale, human review of every AI output is not feasible. Automated output validation pipelines provide a scalable alternative by applying programmatic checks to AI-generated content before it reaches users. These checks can include faithfulness evaluation, assessing whether the response is supported by retrieved context, factual consistency verification against structured data sources, format and schema validation for structured outputs, and statistical anomaly detection for outputs that deviate significantly from expected patterns. More sophisticated approaches use a second language model as an automated fact-checker that queries external sources to verify specific claims in the primary model's output. Combining these automated validation techniques with selective human review for flagged outputs creates a multi-layer quality assurance system. Let us bring together the essential points from our exploration of AI hallucination. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.